So let's actually work on the real example where we are dealing with adiabatic reversible process. And in the beginning, you have a half liter expanded onto 10 liter, right? So your system expand, and what will be your final temperature? And that's the question that we are looking for. And this is an equation that you can use it for crib sheet, or you can find any textbook, so it's perfectly fine. And C is essentially CBM divided by R. So that's you can look it up for what kind of gas do you have inside and so on. And for the argon, the CBM value is 12.47 joule per Kelvin per mole. And if I do the C, which is molar heat capacity divided by gas constant, you know what's the value? It's actually 1.5. I'm expecting this value, right? And if you actually divide this number down, it is very close to 1.5. So that's, you remember the monoatomic ideal gas had only 3 translational degree of freedom, so equivalent contribution to the heat capacity. So it's, this is each, and you got 3 of them. So that's how you got, and divided by R is just a 1.5. I now know my C is here is 1.5. And now this equation, what I can now is V initial, temperature initial to the power of C, and V final, temperature final to the power of C. So this is what I can put it in, and then I want to know what's my final temperature. So I'm going to actually shift this equation into final temperature is, I like to put this one to the other side, so VI, VF. Always, I'm organizing the equation. This is also the practice of this kind of a little bit more math intensive chemistry. When I deal with this, I mean, it's always you will get the right answer, but the precaution to not to make any mistake is trying to come up with the value that is sort of the unitless, and I'm doing this way. So I want to know this, the power of C. So this one goes down, and my choice is not to put it here, not to put it in the middle, but just to do that. So this one divided by this, and then this is a TI. Let me just, to make it easier, to make a focus on this. This is what I need to first write this way, right? You can do that. And then what you need to do is, I am going to get rid of knowing C. This one becomes 1 over C, right? So then all there is nothing but, what's my initial volume? 0.5. What's my final volume? 10. What's my 1 over C? 1.5, 1 over 1 over C, times your temperature, which is 298. Right? So we can calculate this. So this is a pretty simple math to do. But to get here is you need a little bit of the kind of a practice. This was just a little bit of a manipulation of the equation. So then your final temperature, the T final from here is 188. Once you know your final temperature, you are in business. Right? So the question number 1 is, what's your delta T? EFT initial minus 188 minus 298. That is minus 110 Kelvin. So this is a temperature drop, right? Temperature is coming down by 110 degrees if you have that expansion. If the volume change this much. But on top, I can see what's my delta E? CV delta T. I guess now which is N times CVN times delta T. So I guess somebody has to tell me that what's my number of moles of gas. Okay, so here actually this problem says, let's suppose you have 2 moles of gas in this chamber that was smaller volume expand to a larger volume. Then you just have to do 2. And then look at this number, 12.27, multiply by minus 110. And then there will be a unit of joule per, I guess it's just a joule, right? This is just a joule. The answer here is minus 274 joule. That's my Q. Happily 0, right? What's my work? Adiabatic. Reversible here. Well, I don't need to calculate one because I know it's a delta U. Work is, Q is already 0. So therefore, that's the same thing. 274. So this is one thing that I want you to remember. When you want to calculate the work, sometimes you don't need to calculate volume change using the pressure or gains. Those information is not relevant. It's because you have a way to calculate by knowing this relationship between these variables, right? So by knowing that. Okay, so this is an equation, and my next equation that I want to show you is PV is constant. That's for isothermal, right? We probably knows a lot here. And adiabatic, it just has a little hat there, which is called the constant gamma. And once again, the gamma is related to heat capacity now. And gamma is CPM divided by CVM. Okay. If somebody tell me that this is essentially like 1.5 R, do you know what's your gamma value should be? I don't need to give it to you the CPM value, and I'm telling that this is just an ideal gas. Remember this? This one is CVM plus, remember that? R, right? So and that's just a CVM. So what that means is this one, if this is something that is 3/2R, what's your CPM value?
5/2.
2R, so that's 5 divided by 3, which is still bigger than 1, okay? But that's the value you can. So they only give you, many of the problems, they only give you this value. Or the other one, they only give you the value of CPM, and you have to subtract R to calculate your CVM.